Hi everybody, this is Dr. Bricker here with a video for Chapter 18, Part 2. And we can start with this example. So we've got a light bulb is set at the bottom of a 3-meter deep swimming pool, as you can see here. What is the diameter of the circle inside which a duck swimming on the surface could see the light bulb? So the idea is, here's the light bulb down here at the bottom, right here. Now, if you've got a duck swimming on the surface, it's only going to see the light from the light bulb if it could make it into the duck's eye. So let's take a look at this ray here. This ray would come this way, hit the surface, and none of it would actually leave. This is total internal reflection when this happens. This ray comes up and would leave right along the surface, so the duck would have to be in this region here to actually be able to see the light bulb. Kind of like the last example that we did from Part 1. Okay, so let's take a look at this. And again, this is kind of a synopsis of what I've just said. Because of this total internal reflection, you can only see the part here in the middle. Okay, so you can only see the part of the middle, this part here. Darn it, did it again. Anyway, you get the idea from here over to here. Duck has to be there to be able to see this. Okay, so I have to do a little bit of trig, and it says here from the trigonometry, the circle diameter is 2h times the critical angle. So remember, the critical angle is the angle measured from the normal, where anything greater than that angle, we don't see the light. Okay, so in the picture, again, this is the critical angle. We could do a little bit of trig here. The slide just gives you the solution. Where does that actually come from? So if that's the critical angle that I just marked, the tangent of the critical angle, so theta critical, would be the opposite side of the triangle that we're looking at. This is the triangle that we're looking at. So the opposite side would be the diameter divided by 2. So d over 2. So opposite over adjacent. And the adjacent side, that's the side over here, that's h. So if when you do a little bit of algebra, then that's where the formula, this one up here, comes from. You know, multiply both sides by 2h. Tangent theta critical. And that's where d is actually coming from. So just from the definition of what the tangent of theta is. Okay, and then to get the critical angle, we could use the formula for what the critical angle is. So and that's what we have here. The inverse sine of the index of refraction outside of where the ray is originating, and that would be air, divided by 1.33. That's the index of refraction of the water. So look back at the formula for the critical angle. This is how you actually get it. It's a special case of Snell's law. And the critical angle turns out to be 48.7. And then the little added part here is, well, if the critical angle is 48.7, what is the diameter of this region? And that's where the trig part comes into play. Okay, so this is the physics part here, getting what the critical angle is and understanding what that is. And then once you have the critical angle, then probably you would do the second part here to figure out what the diameter of that circle is. Okay, so pretty cool. Anything outside there, the duck's outside of that diameter, the duck does not see the light bulb. The ray never makes it to the duck's eye. Okay, good, and that's kind of a little bit of a synopsis of what I've said there. So fiber optic cable, this is the whole basis of fiber optic cable. Light comes into this tube here, and the index of refraction of glass is greater than the index of refraction of air, which is on the outside in this picture. So light never leaves this tube. I recently got fiber optic cable for my internet here at home. If you ever had any kind of sometimes like a tube they might put down your throat to see what's in your stomach or something like that, this is the whole basis of that too. So to be able to see with the camera, you can send light down this filament, and you know, instead of having to have some kind of operation, doctors could look inside your stomach, for example, and see what you have going on there. Okay, well, pretty neat. So light reaches the end of the tube, the angle of incidence is lower than, and the light can cross the boundary. So over here, light can actually leave. Usually it's just not a glass tube. You might have something outside of it, like this protective cover. Endoscopes, that's the word I was looking for. Make use of this for surgery or just to do some sort of exploring. Okay, excellent. So images formed by refraction. So refraction, again, that's the bending of light. So the reason you see this picture here, this is a ruler in an aquarium, is because the light is being bent, and it does interesting things to objects when the light is coming from the objects. So the rays from the submerged portion refract at the water-air boundary, or in other words, they bend. And then when they get to your eye, it appears they're coming from somewhere else. They're not. This isn't really happening to the ruler. It just, that's your perception, because your brain perceives where the light is coming from to your brain, not where it actually originally originated. Okay, so to your eye, the rays appear to diverge not from the object at point P, but instead from point P prime. So you can take a look at this. Here's the object. This is the actual object. The ray from light comes this way and then bends here. Here's light, again, this ray from the actual object, and hits the interface here between whatever this material is and over here, and the light bends. So it's bending away from the normal. Now you're over here, your eyes will trace these rays back. And where the rays actually trace back to your brain, that's where the image forms. So the object's actually here, but to your brain, it seems like the rays are coming from there. That's the whole idea with the ruler in the aquarium. So it's where your brain perceives the rays to be originating from. That's how you see it. Okay. Okay, so here's the object here at point P. This is called the optical axis here. And we can take a look at a couple of rays. So we're doing a little bit of ray tracing. Here's where the light actually comes from. Hits the interface, bends this way. Here's the object again. Light goes this way, hits the interface between this material and this material, bends away from the normal. And then we can trace these rays back here and here, and then use a little bit of geometry to come up with a relationship between these different distances. So the distance L is common to both the incident and refracted rays, as it says here. Let's take a look and see what that means. So this distance L. So when it says it's common to those, you have L that's associated with this triangle, and then you have L that's associated with this larger triangle. Okay, so if you wanted to look at the tangent of theta for theta 1 and theta 2, we could do that. There's theta 1 and theta 2. So the tangent of theta 1 would be the opposite side. So tangent of theta 1, opposite side, that's L, and then divided by the adjacent side, and it's called S here. So again, this is for theta 1. This is the distance S here. Okay, and then tangent of theta 2, same idea. The opposite side would be L, and then the adjacent side is what they're calling S prime. Okay, it turns out S is the object distance, and then S prime is the image distance. Okay, so these are, what's common to both of these equations is L. So if you solve this one for L, and you solve this one for L, you set them equal to each other, and that's where this comes from. Okay, very good. And then you can form a little ratio here from this equation. So solve for S prime, you get tangent of theta 1 over the tangent of theta 2 is equal to S. And then we could also take a look at Snell's law. This is just Snell's law. You saw this before. So from Snell's law and from this relationship, we can combine those and come up with this using the small angle approximation. So when angles aren't so big, the sine of theta is about equal to the tangent of theta. Okay, so using that approximation, finally you come up with this. So S prime is the image distance. It's equal to N2 over N1. Those are the indices of refraction. N2 is out here, N1 is in here, and then times the object distance. So the object distance is S. Okay, and then you can see that the image appears closer. So if your eye was over here, the image actually appears closer to you. So if you ever go spear fishing and you're standing there with your spear and you're trying to get a fish and it looks to you that it's at one distance, it's actually deeper than that, right? So you would think that the fish is here, your brain, that's where it would perceive it, but really the fish is deeper than it is. Okay, or if you're in a pool this summer, you look at your foot, oh, it seems closer to you than it actually is. Okay. Here's another example we can take a look at. A fish and a sailor look at each other through a 5-centimeter thick glass porthole in a submarine. Okay, so there's a sailor inside the submarine. There's glass between the sailor and the ocean, salt water, glass, and then air. How far behind the surface of the glass does the air bubble appear to the fish and to the sailor? Okay, let me read it one more time. Fish and sailor look at each other, 5-centimeter thick porthole. There appears to be a small bubble right in the center of the glass. Okay, so to the sailor inside the sub, where does this appear? And then to the fish in the ocean, where does it appear? Okay, so we could use this whole idea again to figure out these different distances. It's going to be a different distance for sailor versus fish because the fish is looking at it in salt water, which has a different index of refraction than the sailor, which is looking at it in air. Regardless, the index of refraction of the glass is bigger than water. It's also bigger than bigger than air and also bigger than salt water. Okay, so this is using that equation that we just saw, this equation. This is the image distance for the fish, because this is the index of refraction of salt water. Okay, so you get put the numbers in. To the fish, it seems like it's 2.2 centimeters from the surface to where it's located. And then to the sailor, use a different index of refraction, air, which is 1. Same formula, it's 1.7. Okay, good. So there's a bigger difference between air and water than, air and glass versus water and glass. So the sailor thinks it's even closer than the fish does. Okay, very good. Okay, so the next section then is thin lenses, ray tracing. So there's a couple of ways of solving lens equations and also mirror equations. There's ray tracing, and if you do it carefully, you can come up with a solution that way. Or we're going to have something called the lens maker's equation. That actually works for lenses and mirrors. So each of them will give you the correct answer. Probably the ray tracing is good as an idea to kind of get an idea where the image is going to be formed. But probably you'll use the equation more. So lens is a transparent material used that uses the refraction of light at curved surfaces to form an image, and ray tracing is a way to actually figure out where this image is going to be formed. So a converging lens, that's the kind of lens you see here in the bottom picture, causes the rays to bend towards the axis. So rays come in, they hit the lens, and they're bent towards the axis. So if you were camping and you were going to try to start a fire, you could use this kind of a lens. Now, a diverging lens, thinner in the center than at the edges, light comes in and it's bent away. So there's actually a use for this kind of lens too. It's used as a magnifying glass, or maybe you have reading glasses. That's what a diverging lens would be, and we'll see how that works out in just a minute. Mathematically speaking, converging lenses, you can form a couple of different sorts of images, and we'll talk about those, real and virtual. Diverging lenses, you can only form virtual images. Okay, so in a converging lens, an incoming ray refracts, or in other words bends, this way. So light comes in. Here's an interface between one medium and the glass, for example, and it's bent towards the normal. And then when it leaves again, it's bent away from the normal. And you get a ray that looks like this. So we're going to have three really special rays. One that comes in parallel and bends this way. Turns out it's going to go through a special point called the focus. A ray that comes in and goes right through the center just keeps on going. And then a ray that goes through a point called the focus comes out parallel. And we'll see that in just a minute. Okay, so the way this is happening is it's being refracted at the first surface and then at the second surface again. Okay, so here are parallel rays coming in, hitting the lens, and then they're bent through a special point called the focus. So if you wanted to start a campfire, this is where the rays would be all bent towards, a special place called the focus. There's also one on the other side. Oh, over here as it says. Okay, very good. The focal point on the side from which the light is incident is called the near focal point. So this one's the near focal point. This is the far focal point. They're the same focal distances though. So it doesn't matter if you flip the lens around. Diverging lenses, parallel rays that come in, are all bent away. Here, here, here. So they all spread out. But if you were to trace these all back, they also go through a special point, also called the focus. Okay, so I think conceptually diverging lenses are maybe trickier to understand because you always have to trace the rays back and see where they appear to be coming from. So this thin lens is sort of an idealized situation where the thickness is practically zero. In certain cases, it's not really zero, but for all practical purposes, if you assume it is, you'll get a good result. So the lenses we're talking about and the mirrors, when we talk about those, they're all these idealized lenses and mirrors. Okay, good. So here's parallel rays coming in, going through the focal point. Now if a ray were to come in and go through the focal point, then it comes out parallel. So this is the second important ray. And then the one that goes right through the center just keeps on going. Okay, and we'll use these three rays to be able to construct where the image is formed. Okay, you really only need two, but the third one's a nice check. If rays diverge from an object at point P, it says here, and interact with a lens such that they converge at P prime, we call it a real image. So when the light rays actually hit and form an image, it's called a real image. Not where it appears to be coming. If it really formed an image, that's called a real image. And a virtual image is if that doesn't really happen, the rays don't intersect, but you could trace those rays back and get an image, then it's called a virtual image. It's not really there, it's just that's where your brain thinks it's at. Okay, let me see here. Yep. So let's look at this Christmas tree. Here's the focal point, and as you know from this tree, light is going in all different directions. We just want to analyze a few of these rays. So the one that comes in parallel, this one up here, then hits the lens and then goes to the focal point. The one that goes right through the center here keeps on going. So there's two rays, and that's enough really to know where this thing is located. So it's upside down here. We can look at the third ray. Here's another ray of light that originates from the top of the tree, goes through the focal point, hits the lens, and then it comes out parallel. Okay, so this is actually this is a real image because those rays actually all come together. Okay, we didn't analyze every single ray coming from this. We just picked a convenient spot, and usually what you do is pick the top of the object and do it that way. Okay, so F and F, that's the focal point. S is called the object distance. So S here is the object distance. And then S prime is the image distance. And then H here is the height of the object. H prime is the height of the image. Okay? So as it says here, these rays actually come together. So this is a real image. So all these rays of light converge here. So if you had a lens here and then you wanted to see this actual image, if you put a screen here, so put a screen where this is at, and you would actually see an image form there. So if you noticed from the last slide and this slide, here's the object, Here's a lens. Here's where the image is formed. And it's actually upside down, or in other words, inverted. So inverted images are always real images. So if you're ever going to get a real image, it's always going to be inverted. Those things go together. Okay? So if you did ray tracing on this, just like we had in the last one, you'll see an image like that. So remember, inverted means real. Real means inverted. So those always go together. Okay? So in this slide, you see these rays actually coming together at P prime where the image is formed. That's where you get a nice sharp image. So if your eye were there, you'd see a nice sharp image. If your eye were over here, you would see the image, but it would be not as sharp. Oh, as you can see here. Okay, so you're outside the focal point. Okay, good. And it would be blurry. You'd have to, if your eye were here, say your eye were here and you're trying to look at this, you'd have to move the lens around until you get a nice clear image. Okay, so although you can draw many lines in ray tracing, only 3 are needed, so you can take a look through these. So essentially, the ones I usually look at, the one that comes in parallel, then goes through the lens and goes through the focus. Always use the one that goes through the center because that's the easier one to draw. And then the third one, the ray that goes through the focal point, the near focal point, then hits the lens and comes out parallel. And those should all intersect. Okay? And don't forget, S is the object distance, S prime is the image distance. So we can take a look at this example. A 4 centimeter diameter flower is 200 centimeters from the 50 centimeter focal length lens of a camera. Okay, so we've got a lot of information there. 200 centimeters from it, they're telling you what S is. And they're telling you the focal length. So 50 centimeters is the focal length. Here's a nice picture. And if you did this really carefully with maybe graph paper, you can draw the parallel ray, hits the lens, goes through the focal point. The one that goes right through the center keeps going. Then those rays intersect here. And then to verify everything, you can take a look at the one that goes through the focal point, hits the lens, and then comes out parallel. So where all those 3 intersect, that's where the images actually form. And we see the image is upside down here, so it's inverted. Inverted means real. Okay, we haven't talked about what a virtual image would look like yet. But note here, this object is outside the focal point. By outside, I mean, here's the focal point. It's farther away from the lens than the focal point. Inside the focal point would be here. That's the case where you'll actually get a virtual upright image. Okay, we'll see that in just a minute. But for now, we're forming real images and they're inverted. Okay, so using ray tracing, we can come up with those different distances. And if you did it carefully, you could actually measure S prime, and it turns out to be about 65 centimeters here. Okay. So if you wanted to get a nice clear image, if you put like a note card or an index card or something right here, you would see the image is actually formed there. So before movie theaters used digital projectors, when film would go through, the film would actually go through the projector upside down, and then it would be projected on the screen right side up. So when you're in the audience watching a movie, you'd see a right side up movie, but really what happened is the film went through the machine upside down. That's why you see that. Okay, good. So we can do a little bit with similar triangles here. So this is the similar triangle that we're talking about. This one, and then also this one. Whoops. Okay, so they have a common angle in those two. My drawing's not the best, but I think you can see it. So H prime over S prime, in other words, H prime over S prime is equal to H, that's this, over S. Okay, so then you can come up with H prime. You could try to measure it, but the ratio seems to work better. So this is 1.3 centimeters then. Okay, and the petal is 4 centimeters to begin with. That's this here. Okay, very good. So it's definitely smaller. So we've been able to learn a great deal about the image from this, just looking at the geometry of it. And then in a few minutes, we'll come up with the lensmaker's equation and verify what's going on here. Okay, so magnification, is it bigger, is it smaller? This will actually tell you if it's right side up or upside down. So M here stands for magnification, and it turns out it's equal to minus S prime over S. So S prime and S, those are the, this is the image distance, this is the object distance. Okay, so the minus sign here means it's inverted. So S is always going to be positive. S is always going to be positive. S prime could either be positive or negative. So it's positive when you have a real image, which we have here. And we haven't seen this case yet, but it's negative when it's a virtual image. Again, we haven't seen that yet. So the image that you saw that was formed was on the other side of the lens from where the object was. So you saw, let me go back a slide. Here's the object. Here's the image. They're formed on opposite sides of the lens. So when that happens, S prime is positive. We haven't seen it yet again, but we'll see the case where the image is formed on the same side as the object. Okay, so the magnification here is negative. That just means it's upside down. And it's actually, in this case, it's upside down, so it's negative, but it's also reduced in size, so the magnification is less than 1. Which you could have. You could have it less than 1. The image is smaller than the object, or you could have it greater than 1. It means it's bigger than the object. Okay, now how can you get a virtual image? Well, here's the object here. We're inside the focal length, so we're between the lens and the focal point. Whenever that happens, you're going to get a virtual image. Same 3 rays. The one that comes in parallel goes through the focal point. The one that goes to the center keeps going. So if you look at this ray and this ray, they keep spreading out more and more and more. So if your eye were over here somewhere, your eye were over here. Not the best eye in the world, but if your eye were over there, your eye would trace those rays back. And they trace back. This one traces back to here. This one traces back to here. So to your brain, it seems like the rays are coming from here. And then you can look at the third one also. The one that would seem to be coming through the focal point would head out parallel. Same thing, trace it back. So this is where you get a virtual image. So virtual images are always upright. Okay? And the rays don't actually converge there. Your brain just perceives them from coming from there. Okay? So this is a case where you see that the image here, this is the image, is bigger than the object. So you could use this as a magnifying glass, so things actually would look bigger then. This is the case, I think, where it's harder to understand this maybe because you have to not only draw the rays, but then you have to trace them backwards. Whereas the real inverted images, the rays just ended up there. You already knew where it was just then. Here you have to do a little bit of tracing things back. So this is a virtual image. Virtual images are always upright. Okay. The 3 refracted rays do not converge. They, in fact, diverge. Your brain has to trace them back, and it forms a virtual image. Virtual and upright always go together. This is a case also where S prime is negative. And S prime being negative, virtual, upright, always go together. Okay, so with this ray tracing, lenses, and mirrors, you got to keep track of these signs and what they mean. Okay, now if you look at other sources, other physics books, S and S prime are used a lot, but also people use things like P and Q, different things like that. So it's the same thing. There's no sort of set way, I think, of looking at S and S prime. Okay, here's what it might actually look like if you have a lens like the one that we're talking about. You put it on a keyboard, and the keyboard is blown up. So this is very useful. Okay, very good. So you can still see it. Your brain still perceives it. It's not really there, but your brain perceives that it's there. So it's almost like magic. Okay, so looking at the magnification formula, minus s prime over s. Well, if s prime on its own is negative, you've got a negative sign, s prime is negative, the magnification turns out to be positive. That just means it's upright. And in this picture, it's actually, the magnification is not only positive, but it's greater than 1 because this thing is bigger. Okay, as it says here, we define the image distance to be negative for virtual images. And virtual images are always formed on the same side as the object. So here's a nice picture. Here's where your eye is, and the object is within the focal length. Your eye has to trace the rays back, and then you get the virtual image. Okay, so virtual images, always upright, magnification always then positive. Okay. Good. Here's another example we can take a look at. Here's an object you place here. Notice that you're inside the focal length for this converging lens. To see a flower better, you hold the 6 centimeter focal length magnifying glass 4 centimeters from the flower. Okay, so the focal length is 6, and the image and the object distance is 4. Okay, here's the object. That's the distance from the lens over to the object. And we want to know what's the magnification. Okay, so we could look at the 3 rays. The one that goes in parallel then goes through the focal point. The one that goes through the center keeps going this way. So yeah, you can see they're spreading out. We can do the third one that seems to be coming through the focal point, then goes out parallel like this. So we can trace them back. So your eye is somewhere over here. Trace those 3 rays back, and that's where the image appears to be coming from. Okay, a couple of things here. S, again, that's the object distance. S prime is the image distance. Okay, so we want to know the magnification. We need the formula. I think it's on the next slide. First of all, that's a synopsis of what I've said. Magnification minus S prime over S. So it's a virtual image, so we know that S prime is negative, so we've got the minus sign here. S prime is negative, that's why it's minus 12. We had to come up with that on our own. We know it's a virtual image, so we know S prime is negative, formed on the same side as the object, and then divided by the object distance. So the magnification turns out to be 3. So the object is actually 3 times bigger. So this would just be like the keyboard example. Your eye is over here. You've got this lens. You're trying to look at the keyboard with it, and the image appears bigger to you, and you can actually see it. Okay, image is 3 times as large, and using ray tracing, that looks, if you did this to scale, it looks like it's about 3 times bigger. The other kind of lens we have is a diverging lens. So the one thing about a diverging lens, you can only get one kind of image. You always get a virtual image, and therefore it's always upright. Okay, so converging lens, the one we just looked at, you can get either kind depending on where the object is. If it's outside the focal point, you get a real one. Inside the focal point, you get a virtual one. Diverging lens, on the other hand, you only get a virtual image no matter what. Okay, you can look at these 3 rays. The ones that come in parallel, like this, they're all going to spread out, but they appear to be coming from the near focal point. The ones that are heading towards the focal point leave the diverging lens parallel, and the ones that go through the center, just like the converging lens, just keep on going. So we could use ray tracing. We just need 2 of the 3. Again, I always use the center and then one of the other ones. So you can take a look through these 1 through 6 here, little suggestions. But you just need three rays. Really, you only need 2, and you always have to trace them back with the diverging lens. Again, the nice thing with the converging lens, sometimes if you're outside the focal point, you just do the rays. They come together at the nice point. You don't have to go backwards. This one, you're always going to have to see where they trace back to. Okay, you can use the sun's rays and lens to start a fire. Which one would you have to use? Well, you have to use a converging lens. This is the only one that actually brings the rays together at a point. Okay, so you'd have to use a converging lens for that. Converging lenses are pretty versatile, actually. You could form either type of image, so you could have the rays actually come together, or you could also use it as a magnifying glass. We saw in that case inside the focal length, we formed a virtual image. Okay. So let's see what we have here. A lens produces a sharp focused inverted image on the screen. What will you see if the screen? What will you see on the screen if the lens is removed? Okay, I guess you just have to ask yourself, what if you were standing in front of a lens? You would see yourself upside down. What if you remove the lens? What if the lens was not there? You wouldn't see anything, right? Your image is not going to be magically transported over to the screen, so you wouldn't see anything. It's like stand in front of a wall and see, what do you see? Well, you don't see yourself. You need to have a lens there for this to actually happen. So no image at all. Okay, oh, here's another one. A lens produces a sharp focused inverted image. Okay, so we know it's real because it's inverted. What will we see on the screen if a piece of dark paper is lowered to cover the top half of the lens? Okay, so you're blocking part of it. So part of it's actually going to go, part of the light is actually going to go through. So you will see an image. It's dimmer, but otherwise unchanged. It's just because you're not letting as much light go through. Okay, so light is still going to hit the lens and go this way. It's just we're not going to get as much of it. Okay. A lens produces a sharp focused inverted image on the screen. What we see on the screen if the lens is covered by a dark mask having only a small hole in the center. Okay, so this is really similar to the last question. It's just now even less light is getting through. So you're still going to see an image because the lens is still functioning. It's just you're not going to have as much light hitting it. Okay, yep, good. So the light, even from the top, will still go through this little hole. Just because the rest of it's covered, the one that hits the hole is still going to go through. Which of these ray diagrams is possibly correct? Okay, so let's see what kind of, we've got a converging lens here. The one that goes to the center should keep going, so it can't be A. Same thing, the one that goes to the center would keep going. It's a converging lens, so these rays are coming in and actually spreading out, so it can't be C. Let's see, the one that goes to the center keeps going. So this is a converging lens, so it could be D here. That's how a converging lens would actually behave. Now, if this were a diverging lens here in C, then that might work out. So this is like replace that converging lens with a diverging lens, and you'll get C. Okay, here's another example problem. A diverging lens with the focal length of 50 centimeters is placed 100 centimeters from a flower. Where is the image formed? What is the magnification? Okay, so here's the object. We could use ray tracing, the one that comes in parallel. It's going to spread out, but when you trace it back, it goes here. The ray that goes through the center, that's this one down here, keeps going. And then the one that is heading through the focal point, so it's heading towards the focal point, it goes parallel to the axis. And then when you trace those three back, trace this one back, and then the center one you don't even have to trace back. This is where the actual image is formed. Okay, where is the image? So if you did this carefully, this is 100 centimeters. This looks to be about 25, and that's 50. So somewhere between 25 and 50, probably closer to the 25 here. Okay, so that's what S prime is. That's the image distance. So if you carefully measure that, which maybe they did on the screen here, synopsis of what I've said. So yeah, about 33. That's this distance. Again, if you measured it carefully, you could see that a little bit better. So that's S prime. We know what S is. We know S is 100. Okay, so S prime. The magnitude of S prime is 33. Because it's formed on the same side over here as the object, we know it's actually negative. Okay? We can see that the image is upright, so S prime, that's another way of looking at it, it's negative. Okay, here's the formula, minus S prime over S, so minus, and then S prime is negative 33. Virtual images, S prime is always negative. Whenever the image is on the same side of the lens as the object, S prime is negative. Those always work together. Okay, so this is actually shrunk down. It's positive, which means it's upright. It's less than 1, which means the image is smaller than the object. Okay. Okay, good. So it says here, ray tracing with a diverging lens is somewhat trickier. It is. It's always one more step. You got to draw the rays and then go backwards and see where they come from. So you don't have to do this from scratch every time. Have a little example written down, and you can see how it works out. Okay, and we can take a look at images formed with mirror. Okay, and then we can look at images formed with mirrors. So there's spherical mirrors. They're mirrors cut from what would have been a sphere. Okay, so this is going to be reflection of light here. So curved mirrors can be used to form images, it says here. This mirror is called a concave mirror. So if you're over here, this is sort of like, I think about it walking into a cave. We can look at some rays. A ray that's coming in parallel is going to go through a special point called the focus. So any rays coming in parallel, I'll go through the focus. So this kind of behaves like a converging lens. We're going to see that you can get two kind of images for concave mirrors. You can get a real or a virtual image. So any rays coming in parallel go through a special point. This is a convex mirror. Any parallel rays, and these are all parallel rays, that come in reflect from the mirror, and you could trace these back, and they go through a special point called the focus. Okay, so concave mirrors behave like converging lenses. With concave mirrors, you can get real and virtual images. Convex mirrors behave like diverging lenses. You can only get virtual images. Okay, so again, rays that come in parallel go through a special point called the focus, whether it's rays coming in here or that way. Okay, rays that come through the focus leave parallel. That's our second one. And you could already guess rays that hit the center. This is the center right here. Rays that hit the center leave at the same angle that they came in. So the angle of incidence is equal to the angle of reflection, as it says here. So rays that come in towards the center leave this way. So those three rays you could use to figure out where the actual image is going to be formed. Really, you only need 2 out of the 3. I always go with the one that hits the center, just like I do with the converging lens. Okay? When an object's distance, so same thing, S is the object's distance, greater than the focal length, 3 special rays are enough to locate the position, and really you only need 2 of them. It might look something like this. So here's the one that's coming in parallel, hits the spherical mirror, goes through the focal point. The one that's heading towards the center, that would be this one, leaves with the same angle that it came in with. So that's 2 out of 3. You can see where those cross. Here's the third one, the one that goes through the focal point, hits the mirror and leaves this way. Okay, so you see an image that's inverted. So inverted images are always real. Those always go together. So real and inverted always go together. S is still the object distance. S prime is the image distance. Now with mirrors, this real image is formed on the same side of the object. So that's this is one difference. For mirrors, the real image is formed on the same side as the object. The thing is, though, that it's real. So when it's real here, S prime is positive. So a real image, S prime is positive. Okay? Why is it real? That's where the rays actually come together. So if you took a little note card and you put it here, you get a nice sharp real image. You could use this kind of a mirror to start a campfire, just like you can use a converging lens to start a campfire. Okay, so here's some hints for you. Again, you need 2 out of 3 of the rays. This describes how to actually do that. Okay, and here's an example. So again, h, that's the object height. We're outside the focal point, so here's the part of the mirror. Here's the focal length. By outside of it, I mean inside would be here, located between the focal point and the mirror. We're outside of it. Whenever that happens, you're going to get a real image. Real and inverted, again, always go together. We can look at 3 rays. The one that comes in parallel reflects and then goes through the focal point. The one that's heading through the center reflects with angle of incidence equal to the angle of reflection. And that's enough to know where this is at. We can look at the third one that goes through the focal point and then reflects parallel to the optical axis. And they all come back together here. So you get an image here, because we're outside the focal point. It's going to be a real image. Real images are always inverted. And if you measure this carefully, you could measure what S prime actually is. So S prime is this distance. Okay? It's a real image, so S prime is positive. Okay, very nice. We can get the magnification, same formula, minus S prime over S. So again, the image is real, so S prime by convention is positive. So the magnification is -2. The negative sign means it's inverted, and the 2 means it's twice as big as the image. Okay, very good. And that's what I've said here. So if it's twice as big, it turns out to be a magnitude of 6. Okay, inverted, real always go together. Convex mirrors, just like diverging lenses, a little trickier in my opinion to figure out where the actual image is going to form. Same idea though. Rays that come in parallel are going to reflect, and we could trace them back to where they were going to seem to be coming from. Rays that are heading towards the focal point, so here's one heading towards the focal point. Here's one in the center heading towards the focal point. Here's one up here heading towards the focal point. Those all reflect out back parallel. And then here's the third one, angle of incidence equal to the angle of reflection. So I always use this one, and you can pick your other one, this one or this one. So you need 2 out of 3, and then the third one to kind of confirm. It might look something like this. So here's the object. You can look at the first one that's coming in parallel. It's going to reflect from the mirror. You can trace that back. So it's over here. The one that's heading towards the center, that would be this one, looks like. Yep, heading towards the center, reflects this way, and then you can trace it back here. So your eye is going to be somewhere over here. You're looking and seeing what's happening. And then the one that is the one that's heading towards the focal point, let's see, that would be this one. So this ray is heading towards the focal point. It's going to reflect from the mirror, and it's going to reflect parallel to the optical axis. So when you trace those 3 rays back, trace this one back, this one back, and this one back, this is where the image is actually formed. So it's formed in the mirror. It's literally not in the mirror, but to your brain it seems like it's in the mirror. So you look at this spherical mirror, this looks like the image is actually in there. And you've experienced this before. If you've looked at yourself in the mirror in the morning, it's not a convex mirror, it's a plane mirror, but you see yourself in the mirror. You're literally not there, but your brain doesn't know the difference. It seems like you are there. Okay, so this object here, distance s from the mirror, forms an image here. So this is an upright image, and upright and virtual always go together. Okay, so this is upright, so S prime is negative. So S prime is negative when it's upright. Virtual and upright, again, those always go together. And same thing, you can use the magnification formula to figure out how big this is. So why would you even want to do this? You're making something smaller. Well, this captures a lot more light. So you might have seen this in like a convenience store. They've got a mirror in the corner when you walk in. So if you look at that, it's kept catching light from a whole bunch of different directions. So that's the purpose of this. You have a larger field of vision here. Now on the passenger side of your car, there's a mirror there, and it's farther away from you, so it's actually one of these kind of mirrors. And the reason is you want to be able to see a wider field of vision, so you'd have a some sort of mirror like this. And there's a little warning on the mirror. You'll have to read what it says, but there's a little warning there to take into account. It's closer than it appears or something like that. Okay, so that's the use of it. You know, why would you want to have a smaller image? Well, you get a bigger field of vision here. Okay, so this actually appears to be coming from P prime there. Okay, good. Same thing. You need 2 out of the 3 rays. Pick whichever ones you want. You don't have to do it from scratch every time. Maybe you know, draw a little picture of that scenario. I think that the summary in the chapter actually has that for you. Okay, what do we have here? You see an upright magnified image of your face when you look into a magnifying cosmetic mirror. Okay, it's upright. That means it's virtual. Whenever the image is upright, it's virtual. The image is located, let's see, in front of the mirror surface? No. So virtual is always inside the mirror. Okay, on the mirror surface, behind the mirror surface, only in your mind because it's a virtual image. So behind the mirror surface. So to you, that's where it appears to be coming. That's where the rays appear to be coming from. Oh, okay, maybe this is what I was talking about earlier. The rear view mirror on the driver's side of the car is a plane mirror, while the mirror on the passenger side is convex. Why is that? Oh, here's the reasoning. This is probably a little more eloquent than I said it. Important for the driver to have a wide field of vision from either mirror. You sit closer to the driver's side mirror so it appears large and can reflect a fairly wide view of what's behind. The passenger mirror is quite far from you, at least farther than the one that's right next to you, so it appears relatively small. If it were flat, you'd have a narrower view of what's behind you. So when you make it convex, just like a security mirror, it provides a wider field of view. But the trade-off is you have a smaller image. That's why the passenger side mirror usually contains a warning. Objects in the mirror are closer than they appear. Okay, that's the reason why it's a convex mirror. Okay, very good. So the ray tracing is good. It's kind of a nice check, but once you learn the thin lens equation, you'll probably use that more and then go back and check yourself with these drawings. Okay, we can come up with the thin lens equation. It says lens equation, but it's also good for mirrors. So here's a ray that comes in parallel to the optical axis, goes through the focal point. The one that goes to the center goes here. We could take a look at a couple of similar triangles to come up with the lens equation. So you got a triangle here and a triangle here. And we can look at a couple of distances. This is the focal length here. There's also one on the other side, but this is the focal length. This distance here would be S prime. So S prime is this whole thing. Maybe it's better to look at it here. S prime is this. So if you take that whole distance, subtract out the focal length, you get S prime minus F. That's that distance here. So we're going to look at a couple of similar triangles to come up with the lens equation. Because the two shaded triangles are right triangles, the theta must be the same. The triangles are similar. So the green triangle and the pink triangle are similar triangles. So we can look at ratios. So doing that, H prime over H is equal to S prime minus F over F. So again, look at those triangles. You'll see that you have that relationship. We've also shown before in a previous example, H prime over H is S prime over S. So you can combine those. Essentially, we want to eliminate H prime and H from the previous equation. So we want to eliminate that from the equation. We just want to know what S prime is based on S and F. That's what the lensmaker equation is. So we have this. We have this. We could set those equal to each other. That's what's being done here. And then you could do a little bit of algebra. So from this equation, just divide both sides by S prime. So when you divide the left-hand side by S prime, The s prime cancels out, so you're left with 1 over s. And then divide the right-hand side by s prime, you get this relationship. Put s prime over this and put f over this. You'll see that some things cancel out, and you get the lensmaker's equation. So 1 over s is equal to 1 over f minus 1 over s prime, or you could rewrite it like this. So this is the lensmaker's equation. 1 over s plus 1 over s prime is equal to 1 over f. Now, the only really tricky thing is keeping track of the signs. S is always going to be positive. S prime could be positive or negative. We've talked about that. We'll do some examples of it. And f could also be positive or negative. So f is positive for a converging lens or a concave mirror. F is negative for a diverging lens or a convex mirror. Okay, in the thin lens equation, usually it's called the lensmaker's equation, but thin lens equation, the sign of the focal length can be positive or negative depending on the type of lens or mirror. Here's some conventions here. Converging lens or concave mirror. So this is positive. Diverging lens, convex mirror, this is negative. And then here's some different scenarios. So a real image, S prime is always going to be positive. That means it's real and inverted. And you can see this scenario here. Same thing here. This is a real image. You can tell it's real because it's inverted. That's where the rays actually come together. So both of these right here, S prime is positive. Whenever you get a upright virtual image, that's where S prime is negative. Okay, so it's always negative for these. For converging lens or concave mirror, S prime is positive in this scenario, or it's negative. S prime is negative in that scenario. Here, S prime is always negative. Okay, good. So you got to keep track of that. Maybe make yourself a little table of that. Let's look at this example. A stamp collector uses a magnifying glass which sits 2 centimeters above a stamp. Okay, so that's where the object is. So S, the object distance is 2 centimeters. The magnification is 4. Okay, so that means it must be upright because it's positive, and it's actually greater than 1, so it's larger than it was. The image is larger than the object. What is the focal length of the lens? Okay, so we have the magnification equation. That still works, and now we have the lensmaker's equation. Okay, so you can see it all set up here for you. Here's the picture. This is a converging lens, so we know that the focal length is positive. So be careful. If this were a diverging lens, they might tell you it's a diverging lens and give you the magnitude of the focal length. You know, for a diverging lens, f is negative. That's not what we have here. We have a converging lens. The focal length is positive. Okay, so magnification is +4. We could use this equation here. Actually, let me use the highlighter. We could use this equation here. Magnification is given, and so S prime minus S prime over S. So they're telling you M is 4. Do a little bit of algebra to this equation. Solve for S prime. So when you solve for S prime, you'd have minus M times S. They already put the M in here. So you get minus 8 for S prime. Okay, so that is the image distance. And the negative sign means it's virtual and it's upright. Okay, very good. We could use the lensmaker's equation to figure out anything we wanted to. We know S and S prime, so we can figure out the focal length. So 1 over F is equal to 1 over S plus 1 over S prime. So S was actually given in the problem. That's the 2 centimeters. Now we know S prime from the magnification equation. Just be careful. You got a minus sign here. So you get 1 over f is equal to 0.375, to the minus 1 power. To get the focal length, you just have to take the inverse of that. Okay, and you get 2.7 centimeters then. Okay, so the focal length is greater than 2 because the object has to be inside the focal length. It has to be inside of it if you're going to get a virtual upright image. Kind of like the one we did with the keyboard. Okay, so yeah, very good. So just one more thing. If the focal length is 2.7, being inside it means you're between the lens and 2.7, and you were actually located at 2. Okay. So the rest of the chapter deals with a summary of what we've talked about. So definitely take a look at the homework. You'll get a lot more practice with using the lens maker's equation. And probably start there when you do these thin lenses and spherical mirrors. But then you also have the ray trace you can fall back on and see if things make any sense. Okay, if you have any questions, email me and I'll talk to you later.